Welcome back to a new session of the MOOC on Information Security. Today we will discuss some more details on asymmetric key cryptography and Diffie-Hellman key exchange in particular. Introduction to asymmetric key cryptography. Asymmetric cryptography, also known as public key cryptography, is a process that uses a pair of related keys, one public key and one private key, to encrypt and decrypt a message and protect it from unauthorized access or use. As we mentioned earlier, a public key is a cryptographic key that can be used by any person to encrypt a message so that it can only be decrypted by the intended recipient with their private key. A private key, also known as the secret key, is shared only with key's initiator. When someone wants to send an encrypted message, they can pull the intended recipient's public key from a public directory and use it to encrypt the message before sending it. The recipient of the message can then decrypt the message using their related private key. If the sender encrypts the message using their private key, the message can be decrypted only using that sender's public key, thus authenticating the sender. These encryption and decryption process happen automatically. Users do not need to physically lock and unlock the message. The asymmetric cryptography is shown in the figure. Characteristics of asymmetric encryption. Asymmetric encryption is designed for securing data and key exchanges in public channels. In a nutshell, the purpose of asymmetric key encryption is to serve as a way to securely encrypt data in public channels while also offering authentication and data integrity. Because it doesn't require the exchange of keys, there isn't a key distribution issue that you'd otherwise have with symmetric encryption. Asymmetric encryption keys are large. Asymmetric public and private keys are unique and large strings of random numbers. For example, there are millions of websites using SSL or TLS certificates, and yet each website has a different set of public and private keys. For keys to be strong and secure, however, they must be generated with high entropy or randomness. Each key has to be random and unpredictable enough that it would take modern supercomputers thousands of years to guess. Public key encryption algorithms are strong. The popular algorithms for asymmetric encryption and key exchanges are Diffie-Hellman, RSA, ECDSA, LGAML, and DSA. Although it is not a strict rule, most of the time asymmetric encryption uses long keys that are 1024 bits to 1048 bits or more. In general, the longer the key size, more secure the encryption. For example, if the keys are generated with 2048-bit encryption, there are 2 raised to 2048 possible combinations. It would take modern supercomputers thousands of years to go through so many combinations, find the corresponding private key of a public key. In short, you can't guess the private key from the public key, especially when keys are long. Asymmetric encryption is a resource hogging process. Those massive keys are resource intensive, and that means encryption takes longer to accomplish. In other words, because the key sizes are larger and two separate keys are involved, the encryption and decryption process becomes slower. Applications of asymmetric key cryptography. Asymmetric key cryptography has found use in many authentication domains thanks to its thoroughly identity verification process. Some applications are as follows. First one is digital signature. Verification of document origin and signature authenticity is possible today thanks to asymmetric key cryptography. TLS SSL handshake. Asymmetric key cryptography plays a significant role in verifying website server authenticity, exchanging the necessary encryption keys required, and generating a session using those keys to ensure maximum security, instead of the rather insecure HTTP website format. Another one is cryptocurrency. Asymmetric key cryptography uses blockchain technology to authorize cryptocurrency transactions and maintain the integrity of its decentralized architecture. And the final one is key sharing. This cryptography category can also be used to exchange secret keys for symmetric encryption, since keeping such keys private is of utmost importance in its system. Now we will see the differences between symmetric and asymmetric encryption. Symmetric encryption uses a single key that needs to be shared among the people who need to receive the message, while asymmetric encryption uses a pair of public key and private key to encrypt and decrypt messages when communicating. Symmetric encryption is an old technique, while asymmetric encryption is relatively new. Asymmetric encryption was introduced to complement the inherent problem of the need to share the key in symmetric encryption model, eliminating the need to share the key by using a pair of public and private keys. Asymmetric encryption takes relatively more time than the symmetric encryption. Now we are moving on to Diffie-Hellman key exchange. Whitefield Diffie and Martin Hellman developed Diffie-Hellman key exchange algorithms in 1976 to overcome the problem of key agreement and exchange. It enables the two parties who want to communicate with each other to agree on a symmetric key, a key that can be used for encrypting and decrypting. Note that Diffie-Hellman key exchange algorithm can be used for only key exchange, not for encryption and decryption process. The algorithm is based on mathematical principles. Diffie-Hellman is generally explained by two sample parties, Alice and Bob, initiating a dialogue. Each has a piece of information they want to share, while preserving its secrecy. To do that, they agree on a public piece of benign information that will be mixed with their privileged information as it travels over an insecure channel. Their secrets are mixed with the public information or public key, and as the secrets are exchanged, the information they want to share is commingled with the common secret. As they decipher the other's message, they can extract the public information and, with knowledge of their own secret, deduce the new information that was carried along. While seemingly uncomplicated in this method's description, when long number strings are used for private and public keys, decryption by an outside party trying to eavesdrop is mathematically infeasible even with considerable resources. Diffie-Hellman key exchange algorithm for key generation. The algorithm is based on elliptic curve cryptography, a method of doing public key cryptography based on the algebra structure of elliptic curve over finite fields. The DH also uses the trapdoor function, just like many other ways to do public key cryptography. The simple idea of understanding to the DH algorithm is the following. First, the first party picks two prime numbers, G and P, and tells them to the second party. The second party then picks a secret number, let's call it A, and then it computes GA mod P and sends the result back to its first party. let's call the result capital A. Keep in mind that the secret number is not sent to anyone, only the result is. Then the first party does the same. It selects a secret number B and calculates the result capital B similar to the step 2. Then this result is sent to the second party. The second party takes the received number B and calculates B and small a mod P. The first party takes the received number capital A and calculates AB mod P. This is where it gets interesting. The answer in step 5 is the same as the answer in step 4. This means both parties will get the same answer no matter the order of exponentiation. So, the Diffie-Hellman algorithm is key equal to ya raised to xb mod q. This is same as calculated by B. Then global public elements q is a prime number, a less than q and infinity is the primitive root of q. And key generation for user A, select a private key xa. Here xa is less than q. Now calculation of public key ya, where ya equal to a raised to x capital A mod q. Key generation for user B, select a private key xb. Here xb less than q. Now calculation of public key yb, where yb is equal to a raised to xb mod q. Calculation of secret key by A, key equal to yb raised to xa mod q, and calculation of secret key by B, where key is equal to ya raised to xb mod q. For example, Alice and Bob both use public numbers p equal to 23 and g equal to 5. Alice selected private key small a is 4 and Bob selected small b which is equal to 3 as the private key. Both Alice and Bob now calculate the value of x and y as follows. From Alice side, x equal to 5 raised to 4 mod 23 which is equal to 4, and by Bob y equal to 5 raised to 3 mod 23 which is equal to 10. Now both Alice and Bob exchange public numbers with each other. Alice and Bob now calculate the symmetric keys. Alice calculate it as k equal to y raised to a mod p which is equal to 10 raised to 4 mod 23 which is equal to 18, and by Bob kb equal to x raised to b mod p which is equal to 4 raised to 3 mod 23 which is equal to 18. So, 18 is the shared secret key. Uses of Diffie-Hellman algorithm. Aside from using the algorithm for generating public keys, here are some other places where Diffie-Hellman algorithm can be used. Encryption. The Diffie-Hellman key exchange algorithm can be used to encrypt. One of the first schemes to do is L-gamma encryption. One modern example of it is called integrated encryption scheme, which provides security against chosen plain text and chosen clipboard attacks. Another one is password authenticated agreement. When two parties share a password authenticated key agreement can be used to prevent the man in the middle attack. This key agreement can be in the form of Diffie-Hellman. Secure remote password protocol is a good example that is based on its technique. Forward secrecy. Forward secrecy based protocols can generate new key pairs for each new session, and they can automatically discard them when the session is finished. In these forward secrecy protocols, more often than not, the Diffie-Hellman key exchange is used. Advantages of the Diffie-Hellman algorithm. The sender and receiver don't need any prior knowledge of each other. Once the keys are exchanged, the communication of data can be done through an insecure channel. Another advantage is the sharing of the secret key is safe. The disadvantages of the Diffie-Hellman algorithm are: the algorithm cannot be sued for any asymmetric key exchange. Similarly, it cannot be used for signing digital signature. Since it doesn't authenticate any party in the transmission, the Diffie-Hellman key exchange is susceptible to a man-in-the-middle attack. While considering the security of Diffie-Hellman algorithm, it attacks against the DH protocols comes in a few flavors. The first one is denial of service attacks. Here, the attacker will try to stop Alice and Bob from successfully carrying out the protocol. The attacker can accomplish this in many ways. For example, by deleting the messages that Alice and Bob sent to each other, or by overwhelming the parties with unnecessary computation or communication. Another type is outsider attacks. The attacker tries to disrupt the protocol by, for example, adding, removing, replaying messages so that he gets some interesting knowledge. That is information he could not have gotten by just looking at the public values. Another type of attack is insider attack. It is possible that one of the participants in the DH protocol creates a breakable protocol run on purpose in order to try to gain knowledge about the secret key of his peer. This is an important attack if one of the participants holds a static secret key that is used in many key agreements protocols runs. Note that malicious software could be very successful in mounting this attack. Man-in-the-middle MITM against Diffie-Hellman. A malicious malware that has a MITM or man-in-the-middle position can manipulate the communications between Alice and Bob and break the security of the key exchange. Step-by-step explanation of this process is: in the step 1, selected public numbers P and G. P is a prime number called the modulus and G is called the base. Step 2, selecting private numbers. Let Alice pick a private random number A and let Bob pick a private random number B. Mallory picks two random numbers C and D. Step 3, intercepting public values. Mallory intercepts Alice's public value G raised to A mod P, block it from reaching to Bob, and instead sends Bob her own public value G raised to C mod P. And Mallory intercepts Bob's public value G raised to B mod P, block it from reaching Alice, and instead sends Alice her own public value G raised to D mod P. And in step 4, computing secret key, Alice will compute a key S1 equal to G raised to dA mod P, and Bob will compute a different key S2 which is equal to G raised to CB mod P. And step 5, if Alice uses S1 as a key to encrypt a later message to Bob, Mallory can decrypt it, re-encrypt it using S2 and send it to Bob. Bob and Alice won't notice any problem and may assume their communication is encrypted. But in reality, Mallory can decrypt, read, modify and then re-encrypt all their conversations. So, in this session, an overview of the asymmetric algorithm is given. It is compared with the symmetric algorithm which we learned earlier. An important asymmetric algorithm called Diffie-Hellman algorithm is discussed in detail, considering the applications, advantages and disadvantages. Hope you enjoy this session. See you next time. Until then, bye.